This is The Physics of Aurora Borealis by Jacqueline Malassi. Aurora Borealis is a light phenomenon that occurs in the northern hemisphere, also known as the Northern Lights. In the southern hemisphere, the same event occurs, but by the name of Aurora Australis, also known as the Southern Lights. Essentially, it's lights in the sky that are caused by collisions between charged particles and molecules of gas in the atmosphere, and we really only see them at the poles. The two main physics topics that will be covered in this presentation include light and color and the magnetic field. How does it work? A coronal mass ejection sends charged solar particles from the sun. These particles mainly consist of charged protons and electrons. The charged particles then penetrate the Earth's magnetosphere and cause a substorm, which is a disturbance of the Earth's magnetosphere. The sun-facing side of the magnetosphere contracts inwards and the back end stretches out. The back end is called the magnetotail. When the magnetotail snaps back, the electrons that are near the Earth stream down the magnetic field lines and towards the poles. Why do we only see the lights close to the poles and not at the equator? As seen in the diagram, when electrons head towards the Earth from the Sun, they are deflected at the equator because the magnetic field is perpendicular to the direction of the incoming electrons, which is why from this angle the force would be going into the page, showing how the electrons are deflected in areas closer to the equator. When electrons approach closer to the poles, however, the magnetic field is almost parallel to the direction of the electron's velocity, allowing them to get closer to the atmosphere at the poles. So what causes the color? The ions and electrons that manage to enter the atmosphere via the magnetic field lines excite molecules in our atmosphere. When these molecules get excited, eventually they return to their ground state, releasing a photon, which is a particle of light. Different atoms and molecules will create different colors, so generally the most common are oxygen and nitrogen. Oxygen produces green colors in the sky, and nitrogen produces blue or red. And these colors tend to follow the lines of force in the magnetic field, which is why it sometimes appears like streaming ribbons in the sky. So why do different interactions cause different colors? Well, different atoms emit visible light of distinct wavelengths, and these wavelengths are determined by the specific gas in its electrical state and the energy of the particle colliding with the gas. As you can see in the image below, excited nitrogen makes red colors, while ionized nitrogen makes purple and blue colors. This is entirely dependent on the energy of the particle that collided with the nitrogen. Knowing the wavelength associated with different atoms can not only tell us the type of atom that created the light, but also help us find the frequency of that particular wavelength. On the right is a sample calculation for the frequency of green light. Generally, the green light that oxygen produces when it releases a photon has a wavelength of about 557.7 nanometers. We can use the equation lambda equals the speed of light over frequency to solve for the frequency of this green light and determine it to be about 5.34 times 10 to the 14 hertz. So how does this connect to physics? In physics, we learned about the magnetic field, and we learned that magnetic field lines travel from Earth's northern magnetic pole to its southern magnetic pole, which is actually the geographic southern to the geographic northern pole. This can be explained because the north end of a magnet in a compass is attracted to the south magnetic pole, which is why the south magnetic pole is actually near the northern geographic pole. Understanding the magnetic field has also allowed us to understand why the brightening of Aurora Borealis corresponds to the motion of electrons because they follow the magnetic field lines in our atmosphere. So how does this connect to light and color? Well, as we learned in class, light is electromagnetic, so it makes sense that it responds to solar activity, such as the release of charged particles and their interaction with the Earth's magnetic field. It's also important to have an understanding of what wavelengths produce which colors of light on the visible light spectrum, which are the only colors the human eye can see. Different elements require different amounts of energy to excite its electrons, which is why different colors correspond to different elements. The colors depend on the wavelength of the photon being emitted when the excited atom returns to its ground state. So why is this important? For one, it helps scientists understand the environment of space, which is important seeing that radiation and energy surround the Earth. It's also important for us to better understand the Earth's magnetic field, and we know that it has helped us understand this because we've shown that the lights tend to follow the Earth's magnetic field lines. It also allows us to further study our atmosphere. This is all important because radiation and energy in near-Earth space can have a variety of effects on our satellites, from anything from disrupting their electronics to increasing frictional drag and interrupting our communication or navigation signals like GPS.